Picture this. An animal moves through an open African landscape roughly 1 million years ago. It is bipedal, upright, with legs proportioned almost identically to modern human legs, a relatively hairless body, and a face that would be startling if you passed it on the street, but would be comprehensible as kin once the shock wore off. It is Homo erectus, and it has found something that lightning or a volcanic event has left in its path. A section of forest or grassland is burning. The animal does not run. This is already remarkable. Every other large mammal in the vicinity has departed with impressive urgency in the direction away from fire, but this one stops and watches, and then something falls out of the burning area. Or perhaps a small animal has been caught in the fire and died at its edge. The Homo erectus approaches, tentatively, and investigates, and encounters something that no member of its lineage has experienced in quite this way before: meat that has been transformed by heat into something different from raw meat. Denser on the outside, different in smell, easier to separate from the bone, it eats the cooked food, and in the completely non-dramatic, biologically ordinary way that all the most consequential moments in the history of life on Earth tend to happen, something irreversible has begun. The story of when humans started cooking is also the story of when humans started becoming human. The two events are so deeply entangled that separating them is more of an intellectual exercise than a real distinction. Cooking didn't happen after humans evolved. Cooking is part of how humans evolved. It is the technology that changed the machine that ran it, and understanding how and when it started is one of the most profound questions in the entire study of human origins. The case for cooking as a driver of human evolution, rather than merely a product of it, begins with anatomy, because our bodies carry the evidence of a species that has been cooking for long enough that evolution had time to respond. The human digestive system is, by primate standards, remarkably small. The colon, the large intestine, which in raw food-eating primates does the bulk of fermentation and energy extraction from fibrous plant material, is substantially shorter in humans than in chimpanzees, gorillas, and other great apes. Human stomachs are smaller relative to body size. The overall gut volume of humans is approximately 60% of what would be predicted for a primate of our body size, based on the scaling relationships seen in other apes. This is physiologically unusual. Guts are metabolically expensive tissue. Maintaining the intestinal surface area requires substantial energy, and evolution does not casually reduce them without a compensating benefit. The reduction in human gut size implies that something changed about how the food entering the gut was prepared before it arrived, making it more digestible and reducing the amount of gut processing required. Cooking is that something. Heat denatures proteins, gelatinizes starches, breaks down cell walls, and partially decomposes the chemical structures that make raw food difficult to process. Cooked food is pre-digested in a fundamental sense. The thermal processing does work that would otherwise require the gut to do it, and gut size can accordingly decrease without reducing net caloric extraction. In experiments comparing the caloric yield from cooked versus raw food in animal models, cooked food consistently provides more bioavailable energy from the same starting mass. This means a smaller gut processing cooked food extracts more energy than a larger gut processing raw food from equivalent inputs. The reciprocal side of this trade-off is the brain. The brain is also extraordinarily expensive metabolically. It consumes approximately 20% of total human caloric intake despite representing only 2% of body mass. The evolution of the unusually large human brain required a caloric surplus that a small-gutted, large-brained primate eating raw food could not have sustained. Something had to free up the metabolic resources. The leading candidate, supported by comparative anatomy, fossil evidence, and basic metabolic logic, is cooking. The fossil record provides a timeline that, while imprecise and actively debated among researchers, places the transition to cooking in a specific evolutionary context that gives it explanatory power. Homo erectus appears in the fossil record approximately 1.9 million years ago, and its anatomy is a significant departure from earlier hominins in ways that align with the cooking hypothesis. Compared to Homo habilis and the Australopithecines that preceded it, Homo erectus has substantially smaller teeth, a smaller jaw, a reduced face, and legs proportioned almost identically to modern human legs, longer than any previous hominin, adapted for the kind of long-distance terrestrial locomotion that characterizes human walking and running. The smaller teeth and reduced jaw immediately require explanation, because teeth and jaws in herbivorous and omnivorous primates scale with the toughness and resistance of the food being processed. Gorillas, which eat large volumes of tough plant material, have enormous teeth and massively developed jaw musculature. Chimpanzees, which eat a mixed diet including fruit and some meat, have intermediate jaw development. Homo erectus, which is larger than any of its hominin predecessors and presumably required more total calories, has dramatically smaller jaws and teeth than any ancestor. This makes anatomical sense only if the food was being softened before it entered the mouth. If cooking was pre-processing the food to reduce the mechanical work required for chewing, the legs of Homo erectus suggest another dimension of the cooking story. Long, efficient legs adapted for ground-level locomotion are useful for covering large areas during foraging and hunting, but they also imply a species spending more time on the ground and less time in trees than earlier hominins. Tree climbing is a primary predator escape strategy for non-human primates. A species that has largely abandoned tree climbing as a predator response needs an alternative, and fire, maintained at campsites and potentially carried during movement, provides exactly the predator deterrence that tree sleeping provided for smaller, more arboreal hominins. The direct archaeological evidence for fire use by hominins is a separate thread from the anatomical evidence, and the two threads don't converge on exactly the same date, which is itself scientifically interesting. The oldest unambiguous archaeological evidence for controlled fire, hearths, burned bones showing heat treatment consistent with cooking rather than natural burning, burned stone tools, comes from sites dating to approximately 1 million years ago. Wonderwork Cave in South Africa contains burned plant material and bone fragments at levels associated with Homo erectus occupation, with burning patterns consistent with fire being maintained inside the cave rather than being simply the remnant of a natural fire that swept through the area. The site of Gesher Beno Yaakov in Israel, dating to approximately 790,000 years ago, contains clustered concentrations of burned wood and flint in patterns indicating that fire was being maintained in hearths, deliberate, controlled, sustained fire use, rather than incidentally encountering natural fires. By approximately 400,000 years ago, evidence for fire use becomes consistent across multiple sites and multiple geographic regions. The cave site of Kesem in Israel shows repeated hearth use across an extended occupation period, with burned bone assemblages indicating systematic cooking of animal remains. Sites in Europe associated with archaic human populations show fire evidence with increasing frequency across this period. The gap between the anatomical evidence, which points to cooking beginning around 1.9 million years ago with Homo erectus, and the archaeological evidence, which becomes unambiguous around 1 million years ago, is a genuine puzzle. Several explanations have been proposed. The preservation of fire evidence is inherently poor. Ash disperses, charcoal degrades, and burned bone at outdoor sites can look similar to naturally burned bone from lightning strike fires or wildfires. The absence of preserved fire evidence from a site does not prove fire wasn't used there. It may prove only that the conditions for preserving fire evidence weren't present. The cooking hypothesis for human evolution was most comprehensively developed and defended by primatologist Richard Wrangham, and the hypothesis is worth examining in some detail because it synthesizes a remarkable range of evidence from multiple disciplines. The core claim is that the control of fire and the practice of cooking were not technological add-ons to an already evolved human body plan. They were the selective pressures that drove the anatomical changes distinguishing Homo erectus from its predecessors, and they were the caloric basis that funded the expansion of brain size across the Homo lineage. Without cooking, the metabolic arithmetic of large brain plus small gut doesn't work. The supporting evidence goes beyond the anatomical and archaeological. Human food preferences reveal a species biologically calibrated to cooked food. Humans, unlike other great apes, prefer cooked food to raw food when given a choice. This preference is not learned through cultural conditioning. It appears in infants before extensive exposure to cooked food, and it persists across cultures that have very different dietary traditions. The preference is reflected in smell detection. Humans are extraordinarily sensitive to the aromatic compounds produced by the Maillard reaction and caramelization, the chemical transformations that produce the characteristic smells of roasting and browning. These sensitivities appear to be adaptations calibrated to the detection of cooked food quality rather than raw food quality. The human sleep pattern is also relevant. Humans sleep approximately 7 to 8 hours per night, substantially less than chimpanzees, which sleep approximately 10 hours per night. The extra waking hours in humans allow for more foraging time and more social activity, but they create a window of nighttime vulnerability vulnerability that tree sleeping mitigates. Ground sleeping with fire solves the vulnerability problem. Fire provides the predator deterrence that the trees provided, and the consistent evidence for fire use at hominin campsites aligns with the evolution of the longer wakeful period and shorter sleep duration that characterizes human biology. The social transformation that cooking produced may be as significant as the physiological transformation, and this dimension of the story is less frequently examined than the brain-gut anatomy triad. Cooking requires time. A raw food that can be grabbed and eaten while moving requires no dedicated preparation time. The food is the activity, and the activity ends when the eating ends. Cooked food requires preparing a fire or accessing an existing one, preparing the food for cooking, waiting while cooking occurs, and then eating the cooked product. This time investment changes the relationship between foraging and eating in fundamental ways. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content, covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. When food preparation requires a dedicated time investment, the economics of food acquisition change. The best return on the preparation investment comes from cooking larger quantities rather than smaller ones, which incentivizes hunting or gathering more food than can be immediately consumed raw. The investment in the fire itself also creates a fixed point in space, the campsite with its fire, around which social organization can cohere in ways that purely nomadic raw food foraging doesn't support. The campsite with fire became, in the cooking hypothesis framework, the social anchor of early human groups. It was the place to return to with food, the place where processing and cooking occurred, the place where group members aggregated in the evening before sleep. This spatial anchoring of social life around the cooking fire created the conditions for the elaboration of social bonds, for extended social interaction in the evenings around the fire, for the kind of sustained interpersonal engagement that language development is typically thought to require. The division of labor that cooking enabled also transformed social organization, a group in which some members forage and hunt while others maintain the fire and cook the food that others have brought can extract more total calories per unit of effort than a group in which every individual forage and eats independently. This division is only viable if there are norms of sharing, if the individuals maintaining the fire and cooking receive food from those who hunted and gathered, and if the hunters and gatherers can trust that the cooked food will be available when they return. The cooking fire thus required and reinforced social norms of sharing and reciprocity that are foundational to human social organization. The specific foods that ancient humans cooked first is a question worth examining, because the answer has implications for what cooking made possible that raw food did not. Tubers, underground storage organs of various plant species, are among the most nutritionally important foods that cooking dramatically transforms. Raw tubers are frequently resistant to digestion, with starch in crystalline form that human digestive enzymes cannot efficiently access. Cooked tubers have starch that has been gelatinized by heat, making it far more digestible and providing a dramatically higher caloric yield per unit of consumption. The importance of tubers in early human diets in African environments is supported by multiple lines of evidence, and cooking tubers is the transformation that most dramatically expands their nutritional value. Meat cooking transforms a different set of properties. Raw meat can be eaten and is nutritionally dense, but cooked meat has denatured proteins that are more efficiently digested, reduced pathogen load from bacteria, and parasites that heat kills. And in the case of collagen-rich connective tissue, conversion of tough collagen into gelatin that provides accessible protein from parts of the carcass that would otherwise be difficult to process. The ability to extract nutrition from more of a carcass, including tendons, cartilage, and bone material processed through boiling, expands the caloric return from hunting investment substantially. Plants beyond tubers, many seeds, some leaves, various roots and rhizomes, contain compounds that are toxic or irritating raw, but rendered harmless by cooking. Phytates, lectins, tannins, and various other plant defense compounds are reduced or eliminated by heat processing, expanding the range of plant species that can safely provide nutrition. A species with controlled fire can access nutritional resources from a much broader range of plants than one dependent on raw consumption, effectively expanding the dietary niche available in any given landscape. The mastery of fire as distinct from the opportunistic use of fire deserves its own examination, because these are meaningfully different technological relationships with the same phenomenon. Opportunistic use of fire, approaching a natural fire, warming at it, taking advantage of naturally cooked food at the fire's periphery, carrying an ember from a lightning strike or a volcanic event, requires only the behavioral flexibility to approach and exploit fire rather than flee from it. This is cognitively accessible to a primate with the social learning capacity to observe that fire is exploitable rather than inherently dangerous, and it may predate any active fire making by hundreds of thousands of years. Fire maintenance, keeping a fire burning after it has been acquired from a natural source, requires understanding that fire needs fuel and air to persist, that specific materials burn more effectively than others, and that the fire can be managed through adding fuel and controlling airflow. This is more cognitively demanding than simple opportunistic exploitation, but it is accessible to a species with good causal understanding of object properties and the patience to maintain a fire over extended periods. Fire making, producing fire from scratch rather than maintaining an acquired flame, is a qualitatively different capability. It requires materials prepared specifically for fire starting, a technique for generating the initial ignition through friction or percussion, and the understanding that all of this preparation will eventually produce a fire even before any fire exists. This prospective planning and material preparation is cognitively more demanding still, and its appearance in the archaeological record, inferred from the presence of fire-starting materials and preserved evidence of fire in locations where natural fire sources are absent, may postdate fire use itself by hundreds of thousands of years. The distinction matters because the cooking hypothesis requires only fire use and maintenance, not fire making. A population that could reliably keep fires burning through careful fuel management and ember carrying could cook without ever independently starting a fire. The more demanding cognitive task of fire making may have developed later, building on the established cultural practice of fire maintenance. And the two stages of the relationship with fire may have different evolutionary implications. The question of whether Neanderthals cooked is one of the most debated in the archaeology of the Middle Paleolithic, and it has important implications for understanding the relationship between cooking and cognitive development. Neanderthals had fire. The evidence for this is extensive and consistent across European and Near Eastern sites. Burned bones, hearths, and fire-modified materials appear throughout the Neanderthal archaeological record across their geographic range and time span. What is less clear is whether Neanderthals cooked food in a systematic, deliberate way comparable to the cooking practices of contemporaneous Homo sapiens or of the earlier hominins that the cooking hypothesis positions as habitual cooks from long before Neanderthal times. The chemical evidence from dental calculus, the mineralized plaque deposits preserved on ancient teeth, has begun to provide direct dietary evidence from which inferences about cooking can be drawn. Analysis of Neanderthal dental calculus has identified cooked plant material in some specimens, consistent with cooking, but the picture is variable across specimens and sites, suggesting either that cooking practices varied among Neanderthal populations or that the evidence preservation is uneven. The Neanderthal brain was, as a matter of anatomical fact, comparable to or slightly larger than the modern human brain in total volume. If cooking's primary significance was enabling brain expansion through caloric support, the Neanderthal brain size suggests that they too had access to cooking's caloric benefits, either through independent development or through a shared ancestral tradition going back to Homo heidelbergensis, the likely common ancestor of Neanderthals and modern humans. The most consequential implication of the cooking hypothesis, and the one that links the beginning of cooking to the beginning of humanity in the deepest sense, is the argument that language, complex social life, and eventually civilization all trace back, in a direct causal chain, to the first deliberately maintained fire. The campfire is not just a metaphor for human social gathering. It may be the literal physical origin of the social context in which the selection pressures for language, for complex theory of mind, for the extended social intelligence that characterizes human cognition above all other primate species, first operated at sufficient intensity to drive rapid cognitive evolution, sitting around a fire in the evening, with predators deterred by the flame, with the metabolic demands of digestion being met by the more efficiently processed cooked food consumed earlier, with nothing immediately requiring physical action. This is the context in which social communication could extend beyond the immediate coordination of foraging and threat response into the kind of extended, elaborated, narratively organized social interaction that language enables. The cooking fire created, for the first time in hominin evolutionary history, a social context with enough time, safety, and caloric stability to reward sophisticated communication at levels that pure survival-focused interaction doesn't require or reward. The animal at the edge of the fire, investigating the transformed food with the particular combination of curiosity and caution that characterizes primates encountering novel situations. That animal could not have known what it was starting. No animal ever knows what it's starting. But everything that came after, the reduction in gut size, the expansion in brain size, the smaller jaws and larger legs, the campfires and the social bonds formed around them, the language that developed in the evenings after the cooking was done, the stories and the plans, and eventually the accumulated cultural knowledge that became civilization. All of it runs through that moment of encountering food, transformed by heat, and finding it worth eating. Cooking is not a thing that humans do. It is, according to the most compelling synthesis of the available evidence, something that made humans what they are. The technology changed the biology that used it, and the biology that changed then built more technology. In a spiral that went from a burning landscape in Africa 1 million or more years ago to every kitchen, every restaurant, every campfire, every meal that has ever been prepared with deliberate heat in the history of our lineage. When did humans start cooking? The most accurate answer may be around the same time humans started becoming human. The two things are that deeply connected.